Okay, I'm going to start out by trying to remember what this equation is all about. First thing I'm going to do is just a mathematical manipulation. Is move this v over to the left. PV equals 3/2 n times 1/2 mv squared. And this is going to be the same as PV equals nR times the temperature. Now we're going to be contrasting this with the equation for internal energy of a gas, which is 3/2 nRT. So here's a little bit of a diagram you can imagine, splitting off the internal energy into three parts. Over here is the pressure times volume bit, and over here is the heat. This part is nRT, and this part is 1/2 nRT. You add them together and you get 3/2 nRT. That means if you add energy to a gas, about 2/3 of it is going to be in the form of usable energy that will apply pressure over the outside edges of a volume, and about 1/3 of it is in the form of unusable energy. Although the benefits of thinking about that way I'm not really certain of. Right now I'm just searching for a way of thinking about this that makes sense and is memorable in some way. Or failing that, at least make a list of all the things I should know. For instance, specific heat. What is that? We've been talking about mass specific heat. We're going to start talking about molar specific heat in chapter 12. It is basically governed by the equations Q equals N C sub V delta T. It used to be MC delta T. I think they usually put a P down there. Why did they do that? Oh yeah, it's constant pressure. So we're going to use the same symbol C to represent the specific heat, whether we are doing molar or by mass. Let's solve these for C. C equals Q over N delta T, or M delta T. And the units would be joules per degree Celsius per mole, or kilogram, what have you. So if it takes a lot of heat to raise the temperature, it has a high specific heat, and you can think of that as specific heat capacity. It will hold a lot of heat for a little change in temperature. I guess there's two ways to think of that. You can either say it holds a lot of heat for a little change in temperature, or it takes a lot of heat to change the temperature. And the difference in these ways of thinking of it is, in this case, we're saying the temperature is the cause and the amount of heat it holds is the effect. Whereas if this one, the heat is the cause and the change in temperature is the effect. I bring these both up because I think this way is the more natural way for me to think of it. I don't know about other people, but it seems more natural to me. On the other hand, if you look at the units on specific heat, this way is a better way of thinking of it. Specifically, a larger specific heat is going to result in a higher, or it's going to be harder to change the temperature. And I think that brings us now to talking about C sub V and C sub P. And both of the C's stand for specific heat, and then the V stands for specific heat at constant volume, while this P stands for specific heat at constant pressure. Now the mnemonic for these, basically this one is, imagine being in a balloon. A balloon, with a balloon you can heat the gas inside it, but the pressure on the outside pushing in is going to be relatively constant. The balloon can expand to fill more space or less space depending on what the pressure on the inside of the balloon is, but in general the pressure inside the balloon will match the pressure outside the balloon, or at least fairly close to it. Of course, that's not going to be exact because maybe the stretchy surface of the balloon will apply a little bit more force inward than outward. I'm not really sure how well that holds, really. It would probably depend on how easily stretched the balloon surface was. For instance, in a car tire, if you have 10 pounds per square inch and you have 35 pounds per square inch, the actual tire doesn't grow a whole lot. And essentially the operation of car tire is basically like the operation of a balloon. Now the usual example for specific heat at constant volume of a gas is a pressure cooker. Now unlike with the balloon, which expands fairly easily, the pressure cooker is not going to expand even a little bit. Another point that I wanted to bring up was that solids generally use C sub P, which is the specific heat at constant pressure. If I've got a block of wood or metal sitting around and I heat it with a candle or something, the external pressure doesn't change very much. You could also point out that the volume of the material is not going to change a whole lot. But let's make this a tub full of some kind of liquid that expands a whole lot when it is heated. It would still be C sub P because if it's exposed to the atmosphere, then basically the governing thermodynamic property is the weight of the air above here. Air pushing down on the surface, which results in a pressure. Weight over unit area is pressure. And so that property is not going to change regardless of how much you heat the object. Except, of course, for the fact that it does. We all know about barometric pressure. But in any case, that change in pressure is going to be the least changed of all of the thermodynamic properties. Thermodynamic properties include pressure, volume, temperature, number of particles, and sometimes something called chemical energy. Those are all things that can change in thermal processes. Now, for the question I wanted to answer, which one of these is greater, C sub P or C sub V? So remember, this one's like the pressure cooker, while C sub P is more like a loose balloon. It's exposed to the atmosphere. In fact, I think a lot of times they use hot air balloons in their examples for C sub P, because in that particular case, you've got the bottom of it is being heated directly, and the bottom of it is open and exposed to the atmosphere. Pressure cooker is completely sealed, airtight. Remember, C is measured in joules per degree Celsius per mole. And the idea of using a pressure cooker is you want to make it easier to heat something, so it takes less heat to raise temperature. And the basic thing that means is C sub V is less than C sub P. C sub P then takes more heat to raise the temperature at constant pressure than it does at constant volume. So C sub P is greater than C sub V. Now, as for exactly why and by how much, let's try to get into that in the next video.